Alright, another video here working through some practice problems. This one will focus on strength of acids and molecular properties. I recognize that my microphone may have been rubbing on my shirt and making some background noise, so I'm going to try and hold it and make sure that that doesn't happen and see if I can get that fixed and figured out later. So this is practice problem 18.88 out of your textbook. Choose the stronger acid. So the first one's pretty straightforward. You're going to want to leave yourself some room for this because we are going to be doing a little bit of drawing here later on. But the first one is just comparing HBr or H2SE, selenium. So we can just look at this, choose the stronger acid. Now the straightforward simple answer is which one is the strong acids that we know and which one is not one of the strong acids we know, and that'll be the weaker one. We know HBr is a strong acid. At least in water it acts as a strong acid. So that makes the H2SE, that's not one of the 5 or 6 that I had you memorize. So this makes it the weak acid, and the answer is really done. But if we think about this more from a generalized perspective, if we were to switch the solvents, maybe HBr wouldn't be such a strong acid. So let's take a look at this at more of the molecular view. If we kind of draw a quick Lewis structure for HBr, we'd end up with that, and of course bromine is electronegative, so we'd have a dipole moment pointing towards the bromine, leaving the hydrogen a little bit positive. And just to be complete here, let's draw selenium really quickly. Now, selenium is in the same group as oxygen, so I can kind of guess that it's going to have these 2 lone pairs on it. And it's also going to have some dipoles. And we can just basically see from right here that bromine is more electronegative, so I'll put En for electronegative, and selenium is less electronegative, meaning that in order for this to act as an acid, it's going to have to pull some of that electron density away from that proton. So if we look here at bromine, it's that bond right there that's going to have to be the electrons in that bond will be pulled towards the bromine, which makes it easier for that H plus to leave, versus selenium has less electronegativity to really kind of pull on that bond. It's dealing with this other hydrogen over here, so it can pull on, and again, it doesn't matter which one you choose as long as you're consistent. So let's just pretend that that hydrogen is going to be the one that leaves. That selenium is going to have to pull on those electrons to get that hydrogen able to leave a lot easier, and selenium just isn't as electronegative. The other side of the coin of this is kind of what we talked about. How would it support having the negative charge left over if that hydrogen were to leave? So if we do our arrow pushing mechanism, we say that those electrons leave hydrogen and stay on the selenium, so we end up with a negative charge. If we do the same thing for bromine, if these electrons leave and stay on bromine, we're going to end up with the bromide ion, which just simply has 8 electrons around it and a negative charge. Bromine's more electronegative, so it can support that negative charge a bit easier, so it's much happier being negatively charged like that. So in either case, no matter what, it ends up that the correct answer, and let's change color, let's do this. Let's say HBr is going to be our stronger acid in this case. The next problem is not so straightforward, so let's get these both up here. We have our perchloric acid, so HClO4, or sulfuric acid. Oops. H2SO4. Now we can't just go through and look and say which one's the stronger acid, because these are both strong acids in water. They both dissociate completely. So we need to take the molecular view right away. Let's just make a little note. This is a strong acid in water, and this is also a strong acid in water. So if we were to switch the solvent, then we could kind of start talking about how which one would be the stronger acid in a different solvent. So this is an idea we're really going to kind of not talk about too much. It's in the last chapter of the textbook, 18.8. I encourage you to read that if you want. It's a little bit of a difficult concept to grasp at first, but it's called solvent leveling. where the strongest acid or base you can have in water is water itself, or hydroxide and hydronium. Anything stronger than that, as we've seen, will dissociate completely and form more hydronium or hydroxide. So adding HCl or HClO4 or H2SO4, these are all stronger than hydronium. So they will, when you add them to water, they produce more hydronium. So this is an idea of solvent leveling. So if we want to see if these two are stronger or weaker acids, then we'd have to switch the solvent and see which one now can protonate in that solvent. So that's section 18.8. I encourage you to go read that. But for now, we're going to need to draw the Lewis structures for these. So let's just go ahead and start. Let's draw the full diagram for this. And again, you're probably going to want to leave yourself some room. So I'm going to move this over here, give myself plenty of room. We start with our water and our perchloric acid. And what happens is the lone pair on water is going to grab onto that proton, so the perchloric acid is donating that proton, water is accepting it, so that makes this the base. And of course this is our acid. And what we end up with is a protonated water molecule, so hydronium, H3O+, and we end up with the deprotonated, so we've removed that proton, deprotonated perchloric acid, so this would be called the perchlorate ion. And the strength of this acid is really going to depend on how well that perchlorate ion can support that negative charge it just got from that extra lone pair. So we can look and see that this is going to have a couple resonance forms. So this lone pair, let's just say that lone pair comes down into that bond and it kicks that one up. So we end up with a bunch of resonance structures where now we have this oxygen has the double bond, this one has the extra lone pair. And we can continue this cycle of moving that bond down and jumping these bonds up. Bear with me here while I get all these lone pairs put in. And we're just going to keep moving over. There's one more to draw, so give yourself enough space for one more. So we move that one down. And if we were to keep doing this, we just keep going in circles, so there's really only these four primary resonance structures. So the main idea here is that with these four resonance structures, we've taken that -1 charge that's in the top of the bracket there, and that's been split over 4 different oxygen atoms. So each oxygen carries 1/4 of the negative charge. The more people you have, or the more atoms you have sharing that negative charge, the happier the molecule will be, the more likely it is to go through this process. So we can start to argue that this would be a strong acid, and it is a strong acid, simply because it has these 4 resonance forms to delocalize that negative charge over a larger part of the molecule, which stabilizes the conjugate base. So this is a stable conjugate base, which means it's more likely to give up that proton. If we repeat this same process for our H2SO4, so let's write our water molecule. Sometimes I get questions, how do I know the molecule looks like this, or how did I know to draw it like that? There's 2 answers to that. You should already know how to draw Lewis structures, but in case you forgot, or if you're lazy and you don't want to sit there and count all the electrons, you can simply just Google it. I'd caution you, sometimes the Lewis structures on Google are wrong, so just be careful and make sure you're applying your own principles to understand. So again, in the same fashion, this lone pair is going to go out and grab that proton. So water is accepting the proton there. That makes it a base, and the sulfuric acid is donating it, so that makes it the acid. And we end up with our hydronium again. And our conjugate base of the sulfuric acid, which would be hydrogen sulfate. So we just say it has the one hydrogen now, and we call it hydrogen sulfate, which turns out is diprotic. It has that second proton it can get rid of, so it can donate that proton, and this would actually be a weak acid. But we're just going to stop right there and look at this one. It has a negative charge. And again, we're going to apply the same process. This lone pair can go down and form a double bond and kick that one up. So we end up with this Lewis structure. And I forgot some lone pair electrons back here. And then the other only option is if this lone pair comes down and forces that electron bond or that double bond up into a lone pair. And so we end up with this Lewis structure. So now we've delocalized that negative charge, but we can only do it a third of it, so each oxygen carries a third of the negative charge. Of course, a third is larger than a fourth, so in this case, each oxygen is having to carry more of that negative charge. That makes it less happy. It doesn't like to do that. So in any case, in water, it would still do this. It's still a strong acid. The first proton from sulfuric acid is still a strong acid. But comparing these two, if we had a different solvent, we would see that the perchloric acid is actually the stronger acid because it has more resonance forms. It can delocalize that negative charge over more atoms, which makes it a stronger acid. So that the conjugate base is more stable, makes for a stronger acid. So that's one of the metrics that we use when we look at these. We look at the acid and we see, okay, what's its conjugate base and how can that be stabilized? If it has more stable forms, it's more likely to be the stronger acid. There's one more to this problem. And this one's going to be a little bit easier again. H2SO3 versus H2SO4. And again, we can kind of look at this more straightforward and say, well, this is one of the strong acids that we've memorized. And this one is not, so that makes it weak. And you can also apply that rule of the number of oxygen atoms needs to be 2 times the number of hydrogen atoms. We can see that the sulfite ion, or sulfurous acid, does not meet that, while sulfuric acid does meet that requirement where we have 2 times the number of hydrogen ions. So we can just label it there and we'd pretty much be done. But let's just take a closer look again one more time. And of course my notes has frozen. There we go. And skipping a couple steps, using the same kind of process we just used, we would only be able to draw 2 resonance forms. Whereas with the sulfuric acid, we could draw 3 resonance forms. So the 2 resonance, remember sulfurous acid would look something like this. And I should have drawn it trigonal, but you get the idea. Where we could only really, once we've deprotonated this, the only option we have would be moving that down and moving that up. We can't move it around one more. So this only has 2 resonance forms. Each one of these oxygens, these 2 oxygens, has to share 1/2 of that negative charge, which isn't very favorable. And as we just saw over in this problem, sulfuric acid has 3 resonance forms, so that's 1/3 of the charge. And again, the one with the lower amount of charge shared, or the amount each atom has to carry in that charge, is going to be the favorable version. So we can just very quickly say that the H2SO4 is our strong acid. That's all for that problem. Just a quick recap is that if it's not so straightforward, like the A and C were straightforward, we can just see strong acid versus weak acid, but the reason they're strong is we can look at how the conjugate base carries that negative charge left over once it's been deprotonated. So when in doubt, just kind of look for these resonance forms and try and see if you can figure out how many resonance forms there are. The more ways that it has of spreading that negative charge, or the more electronegative that anion is. So in the first case, this was the more electronegative anion. Generally, the happier it's going to be in that form, and the more readily it's going to form that product. All right.